Hello and welcome everyone to today's Calculus Notes 1.4. We're talking about continuity and one-sided limits today. So first we're going to talk about continuity at a point and on an open interval. So a function f is continuous at x equals c if there are no interruptions in the graph of f at c. So the graph is unbroken, meaning it is without holes, jumps, or gaps. And you can trace it without lifting your pencil. So that's how we can check if something is continuous. So we're going to do this on an open interval. So we're going to use the parentheses here to indicate that, which means we don't actually care what's happening at f of a or at f of b. So here at x equals c, this is continuous if there are no interruptions in the graph. So you can see here that I can trace my pencil without lifting it, and therefore this would be continuous. I'm going to show you a couple examples now that are not continuous. So here is one way on an interval for it to not be continuous. If there is a hole in our function, okay, so you can see right here if x equals c, it is not continuous because we have a gap or a hole. Another way is if we have something like a step function. So now on the interval a through b, we could pick a c right here. And this would not be continuous because if we tried to trace this, we would have to lift our pencil and move it down here to continue tracing it. So this is not continuous. And there's one other example I want to show you. We have a function here. So here, this function is not continuous at c, even though f of c exists, because as we trace this curve, we would have to jump down, plot that point, jump back up, and then keep going. So this is not continuous either. Okay, so in looking at this, there are three mandatory conditions necessary for f to be continuous at a point c. First off, f of c has to be defined. So looking up here, f of c was defined, so it meets that first criteria. Here, f of c was not defined, so already this one fails because f of c is undefined. Here f of c is defined, here f of c is also defined. Now the next thing we need is the limit as x approaches c of f of x exists. So this one right here, the limit exists because it's going towards the same number. Here the limit exists, but we've already said f of c is undefined, so it doesn't matter. In this case, the limit does not exist. Therefore, this cannot be continuous. In this case, our limit does exist, so this one's already met the first two criteria. But let's try the third here. Here it says the limit of f of x as x approaches c is f of c. So a direct substitution is going to work. So in this case, if I plug c in, I'm going to get the same answer as I did for my limit, making this continuous. If we check this last one right here, if I look at my limit, I would get this value, which is not the same as f of c, therefore it doesn't work. So the limit as x approaches c of f of x is not f of c, therefore this is not continuous. Okay, so again, it has to have all three of these for it to be continuous. If it fails any one of them, then it's not going to be continuous. So a function is continuous on an open interval, a, b, if it is continuous at each point in the interval. Okay, so if we look at our interval, if we can pick any c, we can move this around anywhere and all three things are true, then the function is continuous on the interval. Now a function that is continuous on the entire real line is everywhere continuous. Now if f, the function, is not continuous on an open interval, then it has a discontinuity. Okay, now we can categorize these as removable and non-removable. So removable means that if we just take out one point and we redefine one of our values, f of c, then it's removable. Non-removable is not removable. So let's take a look here. So this one is not continuous. What type of discontinuity do we have? This is a removable discontinuity. Okay, and it's removable because if we remove this c and f of c, it becomes not continuous. This next one here where it steps, this is a non-removable discontinuity. Okay, even if we moved f of c up to here to connect with this portion of the graph, it still would not connect it together, and therefore it's non-removable. Okay, what do you think this last one is here? Well, we're coming up to this point, and if we would just move this point right up here, then it would be continuous. So that is a removable discontinuity. All right, let's move on and look at some examples. It says, discuss the continuity of each function. Now we can look at these things analytically as well as graphically. Analytically, we can see that this function is undefined at x equals 0. So right away, if I were to try f of 0, this would not be defined. Therefore, we know this function is not going to be continuous on the whole number line. We can also see here, we have vertical asymptote right there. And so the value we can see is going to be undefined, and the limit also doesn't exist. But it looks like everywhere else it's going to work. So what we would explain this, we would describe the continuity. So is this a removable or non-removable? Well, in this case, this is a non-removable. Discontinuity at x equals 0. All right, we'll try letter B here. Here we have x squared minus 1 over x minus 1. Now, in looking at the graph, it looks like it's a continuous straight line. But we know because of this denominator here, that it's going to be undefined at x equals 1. So right here at x equals 1, there really is a hole. Now, what kind of discontinuity is this? This is a removable discontinuity. At x equals 1. All right, for our next example here, we have two functions, and they're defined over the entire number line. So all values of x are going to work here. So we can just write that the domain is all real numbers. Now, what that tells me is that every f of c is going to be defined. Okay, because any c I plug in, I'm going to get a value. So it passes the first test of f of c being defined. Next, we would want to check about the limit. Now, we know this is a straight line here, and that's going to be continuous. And we know this curve is also going to be continuous. The only place we might wonder about is right there, okay, where this changes functions. But if we look at this, the limit as x approaches 0 of our function h of x equals, well, graphically, it equals 1. Okay, and so because the limit exists, that's great. Now, if we let x equal 0, then we're dealing with this function, and if we do h of 0, we do get 0 plus 1, which is 1. And so because the limit exists and it works by direct substitution, we know this is everywhere continuous. All right, and for our sin x, if we look at this graph here, we can see it's defined over the entire set of real numbers. So the domain is all real numbers. And if we look at this, there's nothing weird that's going to happen. There's no reason to not be able to find a limit anywhere. And so because you can do this by direct substitution every time, we know this is everywhere continuous as well. All right, we're going to move on now to one-sided limits and continuity on a closed interval. When we're talking about one-sided limits, let's just go ahead and draw our function first. And we're actually going to put a non-removable discontinuity here. We'll call that c. So here's our function f of x. And here we are at c. Now, if we want to take the limit from the left, what this is going to be, it's the limit as x approaches c from the left side. Okay. So as we trace this function from the left side, getting closer to c, what is the intended height of the function? Now, in our notation, it's very subtle. The only thing we change is put a minus right here. So that minus symbol means from the left. Now the limit from the right is just what it says. So as x approaches c from the right, what is the intended height of the function? And what the notation is going to be, it's going to have a plus sign right there, and that tells us that it's from the right. Okay, so in looking at this, the limit from the left would be this value right here, and the limit from the right would be this value up here. So let's try our example here. We have a function, the square root of 4 minus x squared. And we want to find the limit of this function as x approaches 2 from the left. So let's practice writing that in our notation. So we write the limit as x approaches 2 from the left. So the left we put minus of our function 4 minus x squared. So we can perform this graphically. So as we approach 2 from the left, right here, so x is going this way, what is our function getting closer and closer to? Well, it looks like 0. If we were to find this numerically, we can make a table of values like we did before, except now all we have to do is make sure the numbers start lower than 2 and get closer to 2. So 1.99 and then 1.999 and then 1.9999, okay, so on and so forth. So we can put this into our graphing calculator. So we have the square root 4 minus x squared. And we'll go to our table. We can see 1.99 gives me, we'll round it, 0.19, 0.06, 0.02. If that's still not good enough for you, you can just keep adding 9s. We added 5 of them, now we see 0.006. Get out a whole bunch. And you can see that we're getting very close to 0. So we're going to say that the limit from the left side is 0. Now in our next example, we have a removable discontinuity here at x equals 0. And here we have the limit as x approaches 0 with the plus sign, so that means from the right. Okay, so here is 0, and here is from the right. So graphically, what is the height of our function intended as we get closer to 0? Well, that looks like 2 to me. If we go ahead and set up our table of values, let's see, we're getting closer to 0 from the right, so we're going to start positive and then get smaller. So 0.01, 0.001, and we could probably just do this one in our head here. So we're going to be greater than 0 here. So it's negative x plus 2, so it's really 2 minus whatever we have up here. 2 minus 0.1 is 1.9, 2 minus 0.01 is 1.99, 2 minus 0.001 is 1.999. And you can see that this is going to our value of 2. Now, why do we talk about right and left limits? Well, because it's important to see as we get close on certain sides, but this is also going to be used in the existence of a limit. So proving whether a limit exists or not. So if the limit from the left doesn't equal the limit from the right, then the limit does not exist. So the limit exists only if the limit from the right and the left are the same. And here is exactly what that's saying in symbols. So our limit equals L if and only if the limit from the left equals L and the limit from the right equals L as well. So we can see here that if we just found the limit at 2, it wouldn't exist because we have nothing from the right. In this case, we know the limit doesn't exist because coming from the left, we get a different value, and so it doesn't work.